Unfortunately, the presence of these organisms is highly dependent on the presence of water. That becomes an issue for a lot of places such as California, where our streams look like this. It's safe to say that our D-frame nets and our rubber waders are no match for a dry stream bed. So without water in our systems, we do not have our aquatic organisms, so what do we do? That brings me to our main question of our research, is how do we assess the ecologic condition of non-perennial rivers during their dry phase? Our non-perennial rivers are made up mainly of intermittent rivers and ephemeral streams. Intermittent rivers generally go dry from weeks to months at a time, while ephemeral streams generally flow for short periods of time after large rain events. This graphic shows intermittent stream length as a percentage of overall stream length across the United States, with the darker colors indicating a higher percentage of intermittent streams. We could see that throughout the West, and especially the arid Southwest, these systems are already very prevalent. As humans place greater stress on water resources and droughts become more common, it's expected that not only the presence of these systems, but the duration of their dry phase will increase, which will effectively decrease our ability to assess them using traditional biomonitoring methods. To begin this research, we wanted to look for a few potential candidate organisms in order to develop metrics. We'd like to have organisms that would have small home ranges in order to detect a localized habitat disturbance rather than getting signal from the uplands in these systems. Also, organisms that are present during the dry phase but could also potentially be responding to aquatic stressors while the stream is flowing. It was also important that we got organisms that would be easily sampled in order to develop logistically feasible and low-cost sampling protocols. From this list, we decided that terrestrial arthropods, both vegetation-dwelling and ground-dwelling, and bryophytes, in this case mosses, were our best candidates. Terrestrial arthropods, extremely diverse group. Many terrestrial arthropods have been used in the past to monitor habitat disturbance, including recent work done by Alicia Stewart, who has indicated that beetles respond to habitat degradation within dry stream beds. Our bugs are also very easy to sample. We use two sampling methods, the first being ramped pitfall traps. Simple design, it's a plastic food container with a hole on either side with metal ramps leading up for the bugs to fall into. We use propylene glycol as a kill agent and preservative in these traps. Our study sites were made up of a 160-meter dry stream reach, which was divided into 8 sampling units. Within each sampling unit, we randomly placed one pitfall trap and deployed it for 24 hours. Our second method is a vegetation beating method, which uses a 1-meter square bag with a drawstring. We would use this bag to cover up vegetation and then hit it with a stick in order to dislodge our arthropod specimens. We would then collect the specimens from the bag and store them in ethanol for later identification. Our second indicator assemblage are the bryophytes, or mosses. So mosses are small, slow-growing plants that could occur in many different habitats, anywhere from arid deserts to aquatic freshwater environments. Mosses have been found to be sensitive to small-scale changes in their environment, which makes them highly suitable for this study. One very interesting aspect of bryophyte ecology is their desiccation tolerance. So bryophytes, when conditions are ideal, will be actively growing, reproducing, and photosynthesizing when moisture is available. But when conditions worsen, they will go into a desiccated dormant state and shut down cellular functions, waiting for conditions to improve. So knowing that these systems during the dry phase would be a very harsh environment for many organisms, our bryophytes could rely on this desiccation tolerance to still be found in the dry channels. We sampled our bryophytes using a floristic habitat sampling method, which uses microhabitats as the main sampling unit. So when we looked at our streams, we separated into 3 main mesohabitats: the dry channel, left bank, and right bank. We would survey each mesohabitat for the presence of these different types of microhabitats, different types of soils, rocks, and logs, and allocated our sampling efforts based upon the types and the abundance of each microhabitat present. We sampled these assemblages between July and August of 2016 in the San Diego region for a total of 39 sites that had already been defined as being reference quality or disturbed, most of the disturbance just coming from agriculture, urbanization, or specific stressors such as cattle grazing. We sampled 15 disturbed sites and 24 reference sites in this study, and you can see through this table that we sampled along environmental gradients. So it was important for us while picking these 39 sites to maximize the environmental variation at our sites, and that's an important point I'll come back to in a few moments. At this time, we've analyzed 92 arthropod metrics. We began by separating out our arthropods into groups by order and then made morphospecies distinctions. The idea behind morphospecies is that we would separate the groups based on morphologic characteristics without using taxonomic keys, and this gave us preliminary species richness counts. We also developed relative richness counts, which is basically the percentage of a certain group as a proportion of the entire site richness as a whole. For our beetles and spiders, we achieved a higher taxonomic resolution in order to develop some functional feeding metrics as well. We have a handful of arthropod metrics which seem to be responding to disturbance. We see on the left that our ant richness at our sites was lower at our disturbed sites than it was at our reference sites. On the right, we see the opposite response actually from our ground spider relative richness. So these ground spiders are the types of spiders that are not using webs to capture their prey. Rather, they're actively hunting, chasing down, and ambushing their prey out in the open. And this is the relative richness, so it's the proportion of this group in relation to the entire species richness of spiders in a site. At this time, we have 39 bryophyte metrics that we've analyzed. We identified our bryophytes down to genus level and also made our morphospecies distinctions. So at this time, we have richness based on family level, genus level, and these morphospecies level richness. We also developed metrics that were specific to the mesohabitats in which we found these bryophytes. We thought that it would be important that because they respond to such small, on such a small habitat scale, that we may be able to see different signals from the bryophytes within the channel than those on the banks. Our bryophytes, interestingly, have shown us that our metric values are higher at most of our disturbed sites here. We see on the left, this is a metric that looks at the family level richness in the channel as a proportion of the overall family level richness of the site. And again, this is higher at our disturbed sites than our reference sites. On the right, this metric is based upon a single family Podiaceae. This was found at almost all of our sites. And this is the proportion of the Podiaceae within the channel habitat as a proportion to the entire richness of the channel. So as I said, this is a current work in progress. We still have a lot of work to do. We're trying to develop a few more arthropod metrics. We're working on identifying our ants right now to get some maybe some additional functional metrics out of those. And we have not yet developed our vegetation metrics, which we're really looking forward to get done. And we're also going to develop a few more bryophyte metrics. So as I said, we sampled along environmental gradients for this study. This is a very important step in metric development to be able to account for natural variation that could be affecting our organisms. Without accounting for this natural variation, we may not be able to see the difference between a response coming from our natural variation in the environment and an actual response to disturbance. A lot of these variables we'll be getting will come from our physical habitat measurements we took in the field and also data from the StreamCat database developed by Ryan Hill with the EPA. So very similar to how we account for this variation with the CSCI and also the physical habitat index that we saw yesterday through Andrew's talk, we will be using random forest models to account for this. This table shows coefficients of determination, or pseudo R-squared. This is early results that we ran models with one predictor variable at a time. This is an example of a few results which this shows that less than 10% of our metric variation is being explained by any of these variables here, where this is an example of 30% of the metric variation within this metric is being explained by our environmental variables. So as we move forward, our random forest models will be using multiple environmental variables as our predictors, and we will use the same threshold of 0.2 as the threshold in which we will the threshold that we will use to account for our metrics. So basically, if greater than 20% of our metric variation is coming from these natural variables, we will adjust the metrics by using the residual value as an adjusted metric score. Just a quick sneak peek. This year we sampled 21 new sites. Main idea here was to increase our sample size and also increase the range of natural variation and the disturbed sites that we had. You can see that we've sampled 5 of these highly modified sites, not the best places to sample overall, but we wanted to expand our disturbance gradient in this study. So while we have not completely answered the question of how do we assess the ecological health in non-perennial systems during the dry phase, we're a step closer. We're trying to work towards this goal here. We have 2 assemblages that we're getting some response from in terms of disturbance, about 10 potentially sensitive metrics, and the next step will be accounting for that natural variation. Quick shout out to all the people that have helped out in this project and sources of funding. A lot of help has come from San Diego, including San Diego Water Board, Chad Laughlin, Rafi Mazer from SWRCB, and also some funding from the Undergraduate Research Opportunity Center at CSU Monterey Bay. Also, a study like this is nothing without a small army of people helping out, not only in the field, but also in the lab, spending many hours looking through bug samples. If you have not already checked out Emma's poster out in the hallway, you could get a hold of Emma. That will give you a little bit more information on how we developed our beetle metrics as well. And with that, I'll take any questions if we have time.
So we have time for a few more questions.
Thanks. I might have missed at the beginning, what the disturbed sites, what characterized a disturbed site?
Just basically percent urbanization, agriculture within the sites, also if we had cattle grazing. A lot of these sites have actually been assessed using CRAM or the CSCI score, so we have these as comparisons of whether or not we're seeing reference conditions or disturbance.
Did the disturbance in any way correlate to changes in the flow regime?
For our metrics?
Or just in terms of comparing between your disturbed and your reference sites, did the disturbed sites have a different flow regime?
That is not something at this point I've looked into. We definitely have a lot of flow data with Chad, with the water board, and that's something that we're going to look into. We'd like to try to account for that flow regime, because potentially we could be seeing responses for how long a stream has been dry. That makes sense for colonization, how much species richness we have there. So we're going to account for that, but at this time I'm not sure if that played a part in the classification of disturbance or reference. Yes?
Wait.
Oh, sorry.
The reference and disturbed metrics, were they the same ones that Pete Odie used and Eric Stein used in their work, or is it?
The classifications of those?
Yeah.
I believe so, because a lot of these sites were sites that we got from the San Diego Water Board that had been sampled previously by them.